What's going on, everyone? You're back with Jono for another quick math lesson. Today we're going to look at applying Pythagoras' theorem to triangles that we're not sure if they're right angled or not. This is a super common type of exam question. You'll be given a triangle and then you'll be asked to prove or justify whether or not it is a right angle. This is a difficult question sometimes for students because it's the first time we've been asked to prove something in mathematics for a lot of us. It's really easy just to say, oh yeah, look at the triangle, tell me if it's right angled, but this is not enough to prove for a fact that it is actually a right angled triangle. Using Pythagoras' theorem, we can actually show algebraically that this triangle is right angled. So some of the typical words you might see with questions like this is something like show that this triangle is right angled, or justify whether or not this triangle is right angled or not. Things like these can sometimes trip students up, especially in an exam, because they go, oh, I don't know what to do. But all this is saying is, can you use Pythagoras' theorem for this set of numbers? So we know for a fact that the sum of the short side squared equals the long side squared, or a squared plus b squared equals c squared. And this happens for every right angle triangle ever. Doesn't matter how you draw it, if it has a right angle, Pythagoras' theorem works. So by that logic, if this does not work, if a squared plus b squared does not equal c squared, we know for a fact that it is not a right angled triangle. So basically this becomes a game of true or false. Do the squares of these two numbers equal the square of the other one? If you can work that out, you can always show or justify that a triangle is or isn't right angled. We've got two methods and both of them work totally fine. The first one is showing that a squared plus b squared does not equal c squared without using square roots. So we've got to work out, is this triangle right angled? The short sides are 8 and 12 and the long side is 16. So what that's saying is that 8 squared plus 12 squared would equal 16 squared if this triangle was right angled. So if I just type both of these two things into my calculator, I can compare the final result. 8 squared plus 12 squared is 208 and 16 squared is 256. Does 208 equal 256? No, this is now a false mathematical sentence, so therefore this is not a right angled triangle. And that is all the proof or justification that you need to show. The second type, you could actually square root the answer and then compare it to the number you were given at the start. So for this one, I've got 3 squared plus 11 squared would have to equal 12 squared. So if I throw this into my calculator, I have 3 squared plus 11 squared is equal to 130. If I square root 130, if this triangle is a right angle, it should give me the answer of 12. But when I throw it into my calculator, I see it's equal to 11.4 something. So that means it is not a right angle because it should be 12. These two things aren't the same. 11.4 and 12 don't match. So that means the whole mathematical sentence is false, meaning it is not a right angle. Sometimes we have an exact figure as our hypotenuse. So that is called a surd, and you might have looked at them before. But in this example, I've got 4 and 7 as my two short sides, and the square root of 65 as my long side. Sometimes my students look at this and freak out. You do not have to change anything with this approach. You just have to see if it works. Still, use your calculator and see what happens. So for this one, I've got 4 squared plus 7 squared has to equal the square root of 65 squared. We don't have to do that right-hand side in our calculator. The square root of 65 squared just equals 65. Square roots and square cancel each other out. So we know that this side is equal to 65. 4 squared plus 7 squared on my calculator is 16 plus 49, which is also equal to 65. That means that this triangle is a right angle because Pythagoras' theorem works for this one. It is a true mathematical sentence. I hope that you guys found this helpful, and I'll see you later.